To present my poster session for the CS236 final project. My project is called High Quality Image Synthesis with Low Latency Generated Model. The idea for this project comes from the fact that most of the state-of-the-art generated model is really expensive when running on a mobile device at the test time. So I'm trying to explore the possibility of running real-time application on mobile device with this generator, but still preserve the high-quality image synthesis results. In order to achieve that, I first need to replicate many features from StyleGAN V1, V2, and V3 to get this high-quality image result first. And then I need to compress the model using a lot of model pruning technique and also the knowledge distillation. In the end, with both optimized model and the original high-quality model, I can analyze the quality and latency trade-off from different module and architectures. To run an experiment, I use two datasets. The first one is the ImageNet docs dataset from the default project. I resized it to 128 by 128 and also did a central cropping. I also used another dataset called FFHQ thumbnails. It's also a dataset with 128 by 128 resolution. To train the model and write the trainer and the architecture, I used the PyTorch 1.10 and also CUDA 11.2 as a default project. So in the experiment, I wrote K image. This means per 1,000 images shown to the discriminator. So the larger this number is, the longer the training session is. When I work on this project, there are a lot of the technical details involved. So for example, in V1, I initially need to implement this progressive growing by upsample the generators results and also merge with previous stage results using alpha. And in the end, I'm able to grow the model from a 4x4 resolution to 128 by 128 resolution. And also, most importantly, I implement this mapping network, which is MLP, to map the entangle latent vector to the style vectors. Also in the synthesis network, I also added this adapted instant norm to help control the styles. So on the right side, the first two rows are the result from StyleGAN V1. You can see the first row is from early stage of training, which only has a resolution of 32 by 32, and the quality is still pretty bad. But when the training get a lot longer to 15,000 K images and to 128 by 128 resolution, the quality got a lot better. However, you might still notice there's some droplet effect near the hair or in the backgrounds. So, getting inspired by V2, we added the weight demodulation and removed the original instant normalization. Another thing I realized that the convergence of StyleGAN V1 is quite slow. So, and also as the paper mentions, this progressive growing limits created some sort of hierarchy positioning for the features. So in order to get rid of this constraint, I also remove the progressive growing in V1 and use the skip generator and residual discriminator for the architectures. In V2 paper, it also mentioned there's some regularization called path length regularization, and also they did laser regulation in order to further optimize the training process to make it faster and less memory consuming. Another interesting and useful trick is from different paper called adaptive discriminator augmentation. So with this, we can improve the quality for the model when the data is pretty limited. For example, the Stanford docs, no, the ImageNet docs dataset is much smaller than FFHQ. So this ADA can help here. In the V3, Astaga V3, there are a lot of changes, but mostly I borrowed the idea from the for the translation equivalent generator. So all the V3 experiment I did are using the Stagan V3 T variant. And so on the right side, you can see like there's the Stagan V3 for dog after 10,000 K images. Also, like after I getting this high quality results, I started model pruning. I reduced the channel and also modified the mapping network for the generator. And but initially the training result isn't quite good. As you can see from the second last row on the right, there are a lot of artifacts around the skin, which makes it quite unnatural. But after adding another distillation, so here the distillation did both like mean square error from the teacher generated output and the student network output, and also have the teacher discriminator to supervise the smaller generator. So with this distillation, we can get a lot better results for the small model, despite it only have 1.5 million parameters. So currently I'm still working on more analysis over the quality and latency trade-off, which I will include in the paper later. Thanks, that's all my presentation.